Okay, this video should not be too bad. We're just gonna take the basic differentiation rules and kind of reverse them. First, just a little bit of review from last chapter. We were looking at finding antiderivatives. So say we started with the function x squared and we want to find its antiderivative. That's the function that when we differentiate it gets us x squared. And we played this little game where we'd say like, well, due to the power rule, it has to have something to do with x cubed, so we'll start with that. We'll take the derivative of x cubed. Okay, that's 3x squared. That's not quite x squared, but but if we just divide both sides by 3, then we'll get it. And so we ended up with the antiderivative of x squared being 1/3 x cubed. And I didn't get into it in the last video, but some of you may have noticed, wait a second, that's not the only function that when we differentiate it, we get x squared. There's actually infinitely many functions that when we differentiate them, they get us x squared. It's 1/3 x cubed plus any constant. And so what we saw last chapter with the antiderivative is it's just the simplest possible function that when we differentiate it gets us x squared. So that's 1/3 x cubed is the antiderivative for x squared. And that's what we used when we were dealing with the fundamental theorem of calculus. So that's what we used last chapter when we were calculating a definite integral. The capital F over here was the antiderivative. We didn't worry about adding any of these constants. Today, we're now going to worry about the constant because we're not just interested in finding the antiderivative. We're now interested in finding what's called the indefinite integral, or we usually just say the integral for short. And in this case, for x squared, it is simply 1/3 x cubed plus c, where c is any arbitrary constant. Okay, and we write it like this. Couple things about it. First of all, it's called an indefinite integral because I'm not sure. I can think of two reasons why actually we might call it that. First, because we have this constant at the end c, and we don't actually know what the constant is. So it has an indefinite value. Or second, because when we saw definite integrals, they had boundaries. There was a lower bound and an upper bound, which are missing in this case. So that's two reasons why we might call it indefinite. Real quick about this letter C, as I said, it is a constant. It is not a variable. It is simply a constant which we don't know the value of. And in most cases, we don't even care what the value of it is. It's just a constant. It's not indeterminate. It's not undefined. It's just an unknown constant. Section A opens up with two rules which should look very familiar because at the end of last video we saw a set of properties of definite integrals and two of them looked just like this. So we have the same properties now for indefinite integrals. If we have a constant multiplied by a function and we want to take the integral of that, we can just take the constant out and just integrate the function. And then if we've got two functions added or subtracted, we can just take their integrals term by term. So first, a problem just like we saw in the last video. We want to find the integral of sine of 2x plus pi over 3. We're going to start this by first taking the derivative of this function that is given to us as a major hint. We take this derivative, we find out, oh, it's negative sine of that thing times 2 because of the chain rule, of course. So we've got -2 sine of this, which is almost what we have here. We just need to divide out by that -2. And therefore, we get this right here, that the integral of sine of 2x plus pi over 3 is equal to -1/2 cosine of 2x plus pi over 3 plus c. And that's what your answers should look like. Don't ever forget the plus c. All right, section A was boring. Let's get into section B. So here we've got all of our integral rules that we need to know. And as I say up top, all of these are found in your data booklet in pages 11 to 13. I would really advise you get out a data booklet right now and find them because some of them are hidden We'll get to that when we need to, but first let's just look through some basics here. Okay, we're integrating a constant. We get out k, that constant multiplied by x plus c. This should make sense because I know when I differentiate this, we get, well, the c is going to, derivative of that will be 0, and the derivative of k times x will just be k. More generally, this is actually a special case of the following one, when we are integrating x to the power of n, as long as n is not equal to -1. If n were equal to -1, then we would have 1 over x, and that has its own rule that we'll discuss in a moment. But otherwise, this is the power rule for integration. We're going to get x to the n plus 1 divided by n plus 1. This should remind you of the derivative rule. With the derivatives of a power, we took the original exponent and multiplied by it, and then we decreased that exponent by 1. Now we're doing the inverse process. We increase the exponent by 1, and we divide by the new exponent. Okay, below that, the e to the x, we know the derivative of e to the x is e to the x, so the integral of e to the x should be e to the x. A whole bunch of trig things should look familiar here. Some fancy ones down here, arc sine, arc cos, arc tan, whatever. Now, 1 over x, the integral of that's going to be ln of x, because we know that the derivative of ln of x is 1 over x. So just be careful of this one. You can't use the power rule in this case. And then you might notice that we've got some absolute values happening here. So let's talk about those on the next page. And yeah, we'll talk about this actual integral as well. So I said that the integrals are all in the data booklet if you know where to look. And what I meant by that is that some of them are hiding in there as derivatives rather than integrals. So we're not going to find in the integral section, oh, the integral of 1 over x times ln of a is log base a absolute value of x. What we will see is the derivative of log base a of x is equal to 1 over x times ln of a. So some of the functions do show up. They're just in the derivative section rather than the integral section. So just use your data booklet wisely. Now, as far as the absolute value is concerned, because that is missing in the data booklet, right? You need to be smart enough if you're integrating this expression to know that here we need to put absolute value around the x. Why is that important? Well, because we can't take the log of a negative. So think about this. If the question were take the derivative of, log of whatever, the thing that's inside of that is going to have to be positive because we can't take a logarithm of a negative number. The question is going to be a defined function for you to differentiate. But now when we're integrating from here, this x could be negative. When we integrate this, we need to make sure to put it into absolute value within the logarithm so that we are specifying that that x there cannot be negative, even if it were in the function that we were integrating. All right, so just be careful of that with your logarithms. All right, so from here, we're just going to go through a bunch of example problems to see how these various rules work out. I really recommend having the formulas in front of you as we go through this if it's your first time seeing this type of thing. So first one, this is just a sum or difference of 3 individual terms, so we're just going to integrate each of them separately. We start with the power rule here. I've got x cubed, so the exponent goes up by 1 to become x to the 4th, and then we divide by 4. 5x, x becomes x squared, and then we divide by 2. Here, that's 2 times x to the 0 becomes 2 times x to the 1. We divide by 1. So it's just, I know they have that as a separate rule on the previous page, but it's really just the power rule. After that, we simplify, and of course, we don't forget the plus c. Second example, we've got 5 times e to the x. You know what? The derivative of 5 times e to the x is 5 times e to the x. The integral of 5 times e to the x is 5 times e to the x. So nothing's going to change there. Here we've got, okay, it's written out with a root here, so we change it to an exponent, 2x to the negative 1/2. Again, power rule. Exponent goes up by 1, So it becomes positive 1/2, and then we're going to divide by 1/2. Dividing by 1/2, same thing as multiplying by 2. So we get a final answer here. Third one, some trig. Okay, integral of sine is going to be negative cosine. Integral of negative cosine is going to be negative sine. Simplify, you're done. Next set. Same thing, let's go. They're just maybe a little bit harder here. Here we're going to see two answers at once, A and B. This is 2 over x. Factor out the negative 2. It's negative 2 times 1 over x. So that's going to be negative 2 times ln of absolute value of x in the answer. And then 3 times e to the x stays the same, plus c. Secant, integral of, or secant squared, I should say. Integral of secant squared is tangent. So we have 3 tangent of x, and then power rule. Exponent 2 goes up by 1 to become 3, and then we divide by 3. Final example over here, secant tangent. I recognize that. The derivative of secant is secant tangent. So this is going to be 2 times secant minus, and then this one here is a little less obvious, but we have 6 over 1 plus x squared. So we look in the data booklet. 1 over 1 plus x squared gives us arctan of x. Next, just more, okay? If you got something crazy like this with a function raised to a power, there's no, like, we can't be using like the chain rule or anything like that on this. You have to expand it. Okay, so use your binomial theorem, expand it out, get a whole bunch of terms, and then integrate each of those terms individually. And if we have a fraction, there's no product rule for integrals. There's no quotient rule. If we have a quotient, you want to just try to simplify that. So simplify here until you no longer have a quotient to deal with, and then again just integrate term by term. We're going to see how to do products later on. The book does give an example of it right away here, again by giving a clue. You know, differentiate this product first to determine what this integral is. I wouldn't bother with this. We're going to learn a technique for this later on in this chapter. It's called integration by parts. You're going to love it. You're probably not going to love it, but that's how I would do a problem like that. We don't need any of these hints. Okay, so this brings us to section C, where we're going to discuss examples where we're going to figure out exactly what the C value is for our indefinite integrals. And they're called initial value problems because we're told extra information about the problem, about like the initial function. So in this first case, all right, we've got a derivative. F prime is equal to this function here, and we're told something about f. F of 0 happens to be equal to 2. This is the key for us to figure out what the C value is. So we start off with our derivative, and then I want to know what f of x is, right? So that means I'm going to integrate. If I integrate f prime, I get f. Okay, on the right-hand side, I need to integrate all of this stuff. Easily done. I'm using my power rule. I got a plus c. So this is a family of functions, f of x, and I want to know a specific function. I want to know really what the value of c is. So I'm going to find the specific function which satisfies this initial condition where f of 0 equals 2. So we just put in 0 for the x's, set this whole thing equal to 2, and then that tells us what the c value is. So we've got a final answer here. There's another example on the right. You can take a look at that on your own. They can be a little more complicated. Here we're given an example with a second derivative, and we're given initial conditions for both the first derivative and the original function. So our second derivative, we integrate it to get our first derivative. Okay, first derivative is equal to the integral of this thing, power rule, power rule, power rule. This is the expression for our first derivative. Now we use our one piece of our initial conditions, f prime of 0 equals -1. And that tells us that c has to equal -1. And now we can integrate again to figure out what f of x is. So integrate that. We get a new constant. They use a different letter here. They use D. If you want to use C again, be my guest. Of course, nobody cares. And then again, we know that f of 1 is equal to 4. So we substitute that in, and then we figure out what D is. So that's cool. The only other kind of twist on something like this, let's say we had the exact same second derivative function, but they gave us different initial conditions. Let's say instead they gave us two pieces of information about the original function. This is not a problem. We do it the same way as before. I'm going to use subscripts for my constants, whatever. So my first derivative, same as before, and 4x cubed minus 4x plus c1. Now I don't have any information about the first derivative to fill in here, so I just got to keep going. I'm going to integrate this to get my original function. So I do that here. Power rule, power rule. The integral of c1 is just c1 times x, and then I have to add on to this another constant. I'm calling it c2. Now I can use my two pieces of my initial values to set up a system of equations, which I could then solve. It's not that hard to do. So you're definitely going to need to practice a bunch of these, obviously, to get comfortable with all the rules. Although I do assure you, it's going to be easier than it was when we were learning the differentiation rules, because you already know those. So you can rely on that prior knowledge to help you work out how to do these problems backwards. You'll still make some mistakes here and there, but I'm sure it's going to be easier than it was the last time around. Now, when we do the next two videos, we're definitely going to have some harder problems. In particular, sections F and G are going to be tough ones, but, you know, we're going to be all right. And to help you out, I really recommend using one of the following three websites, either Wolfram Alpha, Symbolab, or my personal go-to for problems like this, integral-calculator.com. This one's in particular really nice because it even shows you the steps for how to do it. Obviously, right now you don't know what any of these steps mean, but you will in a couple of videos, so don't worry about what's on screen right now. These are going to be wildly helpful for you because your calculator cannot do problems like this. Just like with derivatives, your calculator had no idea how to just calculate a derivative as a function, but it does know how to calculate the derivative at a specific point. Your calculator has no idea how to calculate an integral or an indefinite integral where their answer is a function, but it can calculate the value of a definite integral. If you remember how to do this, then if you go to the same spot, you'll find an option for that. If not, I'll cover it in the next chapter.